Hi guys, can you hear me okay?
Yes,
I'm
sir.
fine.
Okay, great. Awesome. Oops. Sorry guys, I'm having nothing but technical difficulties here, which I think is going to continue.
And then we're going to switch from Zoom because it's unsecure.
What's that?
I said, and then they're going to switch us from Zoom because it's not secure.
Yeah. Is that really
They'll
going
have
to
to
happen?
relearn something else. Who knows? I mean, Google banned it. The Senate banned it. Taiwan banned it.
What? Really?
Yeah.
Oh, I didn't realize that. I knew there was like sort of murmurs of it being banned. Wow. Talk about screwing up a golden opportunity, huh?
Yeah.
No. Well, that's what happens when you get greedy. Okay, guys. Sorry again for the late cancellation on Tuesday. Just had a just to show you that even in the middle of a pandemic, you can have some other health issues show up in the family. But anyway, so what I'm going to do is I am going to just record and put up another lecture this weekend. I was going to do it yesterday, but decided it was going to be too much to do for you guys to catch up doing back to back last night and today. So I'm going to just record another one this weekend, and hopefully that will catch us up. And if you guys have questions, please let me know by email as usual. I am wading my way through the midterms. Still not done. Hopefully, again, I'll be done this weekend. And then hopefully I understand there's a way for me to send the results to you guys via Blackboard. And I'll try to figure that out and get that to you guys. Hopefully you'll have the grades this weekend. Anyway, so I can go back to going back to a week and a half ago. I was going to do a quick review on the delay in logic gates. Is there any sort of general questions, guys?
Yeah. I was wondering what for as far as projects are going to go, have you figured out so we can start preparing for it, because everything's kind of getting piled up, because it seems like all the teachers needed to catch up, but then they are assigning everything last minute. So yeah. I was hoping you had an idea.
Yeah, so what I was going to suggest is for everybody to install LT Spice on their laptops, assuming you guys all have laptops. I don't think it'll work. I don't know if it's going to work for iOS or Android, but I've used it both on Windows and um, the Mac. I have it on my Mac, so I know it works on both of those. So it's just a sort of a free Spice program from Analog Devices. Again, it's called L as in Larry, T as in Tom, Spice. So if you just do a search for it, you can install it. And the project was going to be a simulation project having to do with what we're covering now, so delays and logic gates, etc. So I think if you guys have that installed, and then I can give you guys a quick, I'll probably just record a quick rundown on how to sort of plug in the models for the 180 nanometer TSMC process we have into LT Spice, and just a quick drive. It's reasonably simple to use. Certainly a lot simpler than Cadence, but just yet another thing you'll have to learn. So anyway, that was my thought on using it. If you guys already have PSpice or something else you'd rather use on your computers, you're welcome to do that. I had just tried to install PSpice a few weeks ago, and it was kind of a difficult thing with the licensing and stuff. So it's just going to be a Spice project. The next one, no layout. So I think everybody should be able to do it either with PSpice or LT Spice at home. Did that make sense?
Yeah, I know in our H drive you can get PSpice if you're an engineering student.
Okay, cool. Yeah, either one. If you guys are more familiar with PSpice, that's fine. And just LT Spice is also, that's what I use, just because I couldn't figure out how to get LT Spice, but maybe there's simpler ways to do it. Okay, anything else? Okay, well, I think we're ready to roll then. So I'm just going to do a review on what we talked about in terms of logic gates. So, we talked about this thing called the logical effort, or this ability to, have a delay equation that's a general delay equation that that is a function of this thing called that it's a function of this delay, sort of this should I put it, this non-absolute delay D, which is the absolute delay of the process divided by the the RC time constant of the process, and you'd be given the R and the C for the process, or you'd be able to simulate it just once and then you'd have it forever. And then after that, just by looking at the circuit topology and the loading on the circuit, etc., you could come up with equations for the delay. So the concept was the delay has two components. One of them is P, which is the, oops, sorry guys. One of them is P, which is the parasitic delay, which is the delay of the device itself. And one of them is F, which is a combination of the topology of the gate, which is G. So if you remember, each gate has its own G. So for an inverter, it's just G is 1. For I think a 2-input NAND gate, it was 4/3, and so on. And then H is basically the fan out, which is the relationship between the capacitive load you're driving and your own input capacitance. And so I think this says the same kind of stuff. Okay, parasitic, okay. And, you know, you get these curves, which is just those equations. And again, the nice thing is that, you know, we just have to do this once. And so these are the G's for different gates. So, you know, an inverter is 1, 2 input, NAND gate, again, it's 4/3, 2 input NOR gate, it's 5/3, so on and so forth. So you only need to do this once because it's a topology thing. And these are ratios between this device's drive capability and that of an inverter that's similarly sized. And then you'd all same with the parasitic delay. Again, these are ratios between the parasitic delays of this gate and the parasitic delay of a similarly sized inverter. Okay, so you only have to do this once, and then you can use it in, you know, the circuit we worked on this in this ring oscillator, and which is something people put together to figure out the speed of, you know, their silicon chip, which is a chain of inverters that are just going to be oscillating. So let's say typically they're in the 30s or 40, sorry, they're always odd number of stages. So it'd be like, you know, a 31 stage ring oscillator or 33 or a 41 or something like that. So that will actually oscillate. And, you know, we use that as an example to calculate all this stuff. So the logical effort, the G for an inverter is 1. So all these things are inverters. They're all driving another inverter like themselves. So the H, or the fan out, was also 1. And the parasitic delay for an inverter from our table was also 1. So basically you end up using that equation. So G times H is 1 plus P, and P is 1, so you end up with a D of 2. And that 2 gets multiplied by the 3 RC, or the tau of whatever process you're in. So, you know, the frequency this was a function of just the circuit, how many stages you had, and so on. So, you know, depending on the process, you'd have a different frequency. Okay, a similar model for a fan out of 4 inverter. Again, the logical model G was 1 because they're all inverters. Electrical effort in this case was 4 because you're driving 4 devices like yourself. So the ratio of what you're driving in terms of the capacitance to your own input capacitance is 4. And the parasitic delay is still 1 because that's just your own parasitic. And so the delay ends up being G times H, which is 4, plus P, which is 1. So you'd end up with a delay of 5. And then that again would get multiplied by 3 RC, and that RC being the RC for the process that you're in. And again, you know, so if you're in a 0.6 micron process, it's a much longer delay than a 65 nanometer process. But in both cases, you just have this delay of D of 5, but you just multiply that by a different tau or time constant for the process. It's kind of a nice system for figuring this out. But really, it's just the starting point for using this thing for multiple stages. So this is everything we've done right so far has been figuring out the delay essentially of a single stage, but the real power of this way of looking at things comes in multiple stage systems. So for example, you have this case, whoops, sorry guys. Let's say you have this case where you have multiple gates. So you have 4 gates because you know you need this functionality, and you know eventually you have a certain load that you need to drive, and you have a certain load that the previous stage can drive, and you want to figure out how to size these things. Okay, so you can use a logical effort for the whole network. And today we're going to talk about how to analyze that. You know, there's always this temptation for designers. I'm going to give you guys like, why wouldn't we just simulate this thing in Spice, right? So, and that's always a temptation, especially with new designers. But the problem is, usually the problem you're given is it's kind of more open-ended. So the problem is typically, you have a certain functionality, you have to drive a certain load, and you want to figure out, what's the fastest circuit topology, and, how do you size the gates to get the delay you need, or the minimum delay. And if you're just simulating, you can just simulate. All a simulator can do is to show you how fast a particular implementation is going to operate, and you can sort of tweak that up and down, but it doesn't tell you, what's the optimal implementation, and doesn't give you any insight. So it's really useful to have something like this logical effort as a starting point for your simulation. So in fact, the project I have in mind to give you guys is basically, coming up with, it'll be a comparison between simulating a multi-stage network compared to doing the hand calculations, and sort of the insights that you would get in either case. Okay, so now that was the idea behind why we're doing this logical, multi-stage logic networks, why we're analyzing it with this logical effort path. So basically, we remember that we had this, this delay was for a single gate. Excuse me. Was G times H. So G was the logical effort. So for, let's say, a NAND gate. NAND 2, this was 4/3. H was our fan out or loading plus P, which was the parasitic delay. So this was for a single gate. Okay. Now, if you have a multi-stage network, let's say an overall network, you can have a corresponding G, which is sort of a capital G, which is basically all the logical effort of each stage multiplied by each other. Okay, so let's say you had remember that, let's say if you had a 2-input NAND gate followed by a 2-input NOR gate. So remember that the G of this guy was 4/3, and the G of this guy was 5/3. So the overall, the path effort would be 4/3 times 5/3. So that would be this path logical effort. Okay, and the path electrical effort would be the output capacitance divided by the input capacitance of the path. So again, in this simple case, you would have an output capacitance that you have to drive, and then you have your input capacitance that the previous stage has to drive. Okay, and then you have this path effort, which is multiplication of each stage's G times H. So again, here you would have, a G of 1 for the inverter, 2 for the NOR, 5/3 for the NOR gate, 4/3 for the NAND gate, 1 for the inverter. Okay, you'd multiply all those up and get capital G, and you have the capacitance of 20 units, say, on the output, and a capacitance of, say, 10 units on the input, and that's your capital H, okay? And then there's a path effort, which is each one of these. Now, we don't know, notice, well, this is sort of not capital G. This F is not equal to capital G times capital H. It's each GH times GHs. And we'll see why that's the case. There's like a reason. At this point, it seems like it should be the same thing, but it's not. But anyway, so that's what we're starting with. And so, the question is, can you just write G times capital H? And the answer is no. No. And that's because you can have something like, let me go back to, well, we don't have that situation here, okay? But let's say if you had the situation where this thing would need to drive 2 inverters of a certain size, and so this would not be the same as, so in that case, this GIHI would not equal to capital G capital H, and we can show that. So let's say you have this case where you have one inverter, you want to know the best delay through this path, but there's this other path that also exists. It just, it's doing something else, okay? So looking at that, so, the G for all of these individual inverters is 1. So capital G, which is, say G, and I want to look at this path. So I'm going to call this G1, I'm going to call this G2, and I'm going to call this G3. So that's G1 times G2. So 1 times 1 is equal to 1. Okay. Now H is the capacitance on the output divided by the capacitance of the input. So it's it should be, so H is actually is 90 divided by 5. Okay, is equal to 18. Okay, and G times H is 18 times 1 is equal to 18. Okay, so that's G times H. And now we want to see if this is the same as the other way of doing it. So let's look at each individual path, right? So if you look at H1, okay, of this guy, it's the capacitance of the output divided, this is the capacitance of this node divided by the capacitance of the input. So capacitance of the input is 5. Okay, it's simple enough. But the capacitance of the output of this is the capacitance of this guy plus the capacitance of that guy. It's not just one of them. So it's 15 plus 15. Oops, sorry guys. And H2 is just 90 divided by 15. So that's equal to 6. Okay. So G, if I calculate F as G1 H1 times G2 H2, so again, G1, G2 are both 1, so it really ends up being H1 times H2, so 6 times 6 is equal to 36. Okay, so immediately you can see that you know, this way of calculating f gives us 36. And if you try to say this, f is equal to g of h, you would get a different number, 18. So those are not the same. Okay, did everybody follow me? So in this case, you're saying g times h, and in this case, you're saying a multiplication of g times h's. Okay, and as soon as you have this branching of your path, this capital G times h and this equation don't equal to each other.
Professor?
Yeah.
For H1, how did you get 15 plus 15 again? And in H2, why is it just 90 divided by 15?
Okay, so let's see. So, whoops, what happened? Sorry, guys, I'm having nothing but technical difficulties here. I have to reshare my. Okay, so the question was for H1, well, how did we end up 15 plus 15? So H1, how is it 15 by 15 divided by 5? So the definition of H1, so that's the fan out for this first stage, okay, is the output capacitance over the input capacitance. Okay, just think of it as units now. And so when you look at the output capacitance of this guy, you'll see two capacitance. One of them is this inverter with a 15x sort of capacitance. But then you also have the capacitance of the second inverter that's in your path for also 15 units. Okay, so does that make sense why you end up with the output capacitance is 15 plus 15?
Yeah, so
Okay.
I see the output is like 15, C out over Cn, 15 plus 15 over 5. So then H2 is also why I was curious about that too.
Yeah, so the H2, you have 90 for the output. So this is this stage here. So you have 90 for the output and you have 15 for the input. So you end up with 90 divided by 15 for H2.
Okay, so it's like per stage then, is that what we're looking
Yeah,
at? Okay,
yeah,
okay,
exactly.
thanks.
Yeah. So for each stage, you're really looking at that. Can I erase, please? No, why did I do that? Touched the wrong button. Sorry, guys. Hello. Nope. Sorry, guys. My equipment is not cooperating. Okay. Nope. Never mind. Okay, so I was trying to erase something here. So sorry, I can't seem to be able to erase. So anyway, so yeah, it's all the small g and small h is always for that single stage. So it's all kind of local. So if I go back, God, let's see. If we look at here, so this thing's G times H is just, you don't know, you're basically being asked, how do I figure out the input capacitance of this guy? What's the ideal input capacitance? But the H would be the output capacitance divided by its input capacitance. So in each case, it's sort of a local H. Any other questions? Okay, so basically so this thing means that we have to introduce this new concept called branching effort, okay? And this basically says that, let's say you have this path, you wanna get the ideal delay of, so basically you're interested in this path, You also, if you have to make sure if there's a branch off of any of these nodes that, or just happens to be loading down the path, but not part of the path that you're interested in, you also have to account for them. And basically you end up with this thing called B, which is this branching effort. And it's really simply the sum of the on path. So in this case, it'd be like this would be an on path capacitance here, okay, plus the off path capacitance. So this is sort of the off path capacitance. If this was B1, it would be, the capacitance of this top inverter plus the capacitance of the bottom NAND gate. And you divide that by just the capacitance of the NAND gate that you're interested in. So C on path plus C off path over C on path. Okay, and for the whole network, it's the multiplication of those. Okay, so now with that, we can, as long as we have calculated this capital B, now we can say F is equal to G times H times B. Okay, so now we can actually use this this equation to describe the delay. Okay, and so basically, let me just do some bookkeeping here. So this is defining a few things, and you guys will see how this gets used. So we have the path effort delay, which is the sum of all the G's and H's. So this is, so for example, this would be G1 H1 plus G2 H2, etc. Okay, and we have the path parasitic delay of the, so this would be P1 plus P2 plus P3, da da da. And then the total delay is, these two things. Okay, so that's pretty simple, makes sense. You get the effort, the logical effort delay of each stage, and the total delay is just the sum of those. Okay, again, let's just talk about designing just the circuit for the fastest possible function. Okay, so again, the path delay, this is the total delay of your path, is the sum of all the delays. So if you just had, a inverter driving a NAND gate, it would be the delay of this plus the delay of that, and the components of this would be the G1 H1 plus P1 here, and the components of this would be the G2 H2 plus that parasitic. And then we're saying you can just sort of split this up, so the overall delay would be G1 H1 plus G2 H2 plus P1 plus P2. Okay, so it's kind of stating the obvious. And so that's the overall delay. We want to figure out how to optimize that function, right? That tells us the fastest time we can go through a particular path. Okay, so the next thing I'm going to claim, which is a mathematical, I guess, mathematical rule or a rule of thumb, I'm not sure what it is, but basically this thing that if you have the sum of a set of numbers whose product is constant is minimized by choosing all the numbers to be equal. Oops, I jump here. So meaning this, right, that if you have this like an F function, right, that's a total delay of n stages, right? So this F is, let's say it's got 3 stages. Okay, I'm going to say that this number f, because it's constant, right? So it's a question of how this f is best divided between these three. So why is f constant? Is because let's say this is the function that you were trying to implement. Again, I'm just going to come up with a random function. So notice that regardless of what happens, so we want to see how we're going to size these individual components, right? How do we size these things? Given that we know our load at the output, we know we have a certain input capacitance disallowed, and we know this functionality we need. We need an inverter, a NAND gate, and a NOR gate. Okay, so here the F is going to be GBH. Okay, so there's no, for the sake of discussion, I don't have any branches here, so I've made the branching effort to be 1. Okay, so it basically ends up being G times H. The G is, the G's of these individual ones, so it's G1, G2, G3, which is, 1 times 4/3 times 5/3. Again, this is for a NAND 2, this is for a NOR 2 and an inverter, okay? And H is C load over CN. Okay, so I know all that. So F is constant. Now I want to figure out what's the best way to size these individual gates to minimize the delay through this path. So that's the question. And what we're claiming is when F is a known constant and is made up of these 3 things, the most optimal solution is to make each one of these 3 things the same number. And so that is just, so I guess you're gonna have to trust me, and I've trusted the literature here is that the best way is to choose all those numbers to be equal. So basically you want F1 equal to F2 is equal to F3 would give you the minimum number for F as a delay. And basically what that means is this is the F for each stage is F, which is again is known, right? Once you know the functionality of the path and the output load and the input load, you know the F, okay? And you have 3 stages. So 1, 2, 3 in the stage. So basically the delay or the logical effort per stage, which is this F hat, is this F times 1 over n to the power of that. So basically there you've divided this F into the delay for each one of these stages. And you're saying it's going to be the same, okay, to minimize the delay. Did that make sense? That was like a real tortured explanation. But basically, we're trying to minimize D by saying the best ways to spread the delay is to sort of the effort delay to be the same for each stage. All right, so let me know if that doesn't make sense. Okay, but anyway, that's like the main point of the logical effort. And let's see how, so again, we're finding this is the way to find the fastest delay, or this is your fastest delay, and we don't need the individual gate sizes. We just need to know the functionality and the output load and the input load. Now let's look at how we're going to use this to calculate this delay. Okay, so let's say this is the problem we have, right? That we have a we know we need this functionality, so that we have this network, and we want to know how to minimize the delay from A to B. And we also know that we have these extra loads that are the branching delays that's slowing things down. We want to know how to size these devices. We know the size of the first NAND gate, but we want to figure out how to best size the second NAND gate and the NOR gate. Okay, so let's look through what we want to do. So let's first look at what the logical effort here is. Okay, so that's capital G. Okay, which is we said it's GI or G1. Let me actually move this now. I can't move it. So G1 times G2 times G3. Okay. So let's see. So this would be G1. This is G2. This is G3. Okay. So I just remember, you guys can look at the table again. For a 2-input NAND gate, G1 is 4/3. Actually, I don't remember a 3-input. So I think a 3-input NAND gate is 5/3. And a NOR gate is also 5/3. So this ends up being 4/3 times 5/3 times 5/3, which is 100/27. Okay. So that's the capital G. Okay. The electrical effort is capital H, which is the capacitance of the output over the capacitance of the input, and the capacitance of the output happens to be 45, you know that, and the input capacitance is 8. Okay, so that's capital H. Okay, so the branching effort. So we said it's the multiplication of the branches, and each B was the on path capacitance plus the off path capacitance divided by the on path capacitance. On path. Okay, so let's look at this B1 first. So this ends up being B1 times B2. Okay, so this is B1, this would be B2. Okay, so in this B1 case, you're driving 3 loads. Okay, so that the off path is 2, the on path is 1, and the on path is 1. So it ends up, so B1 is the off path is 2 plus on path is 1 divided by 1, or 3, times for B2, again the off path is 1. So these are conveniently like the same gate. Doesn't have to be that case, but it just helps us with figuring out this branching effort easily. So the off path is 1 plus the on path is 1 divided by on path. So this ends up being 2. Okay, so that ends up being 6 is our branching effort, capital B. Okay, so our path effort, remember this is capital F, is G times B times H. Okay, so G is 100/27, calculated up here, times H is 45 divided by 8 times B, sorry, I put those out of sequence, times B is 6. Okay, and I multiply all those things up, I end up with 125. is the path effort. Okay, so this should all be pretty straightforward. Does this make sense to everybody right up till I got 125 for capital F? How I did that? So notice again that we didn't get into what the sizes X and Y. We didn't really need to do that to get to capital F. And that's what we want to figure out, how do we size X and Y? Okay, but we basically just used the functionality, which is the type of gates we had, the output capacitance and the input capacitance, and the number of branches to get up to this 125. Okay, so next thing we want to know is...
Actually, Professor, I have a question.
Yeah, go ahead.
I didn't quite catch how you calculated the G1, G2, and G3.
Sure, it's basically like if you go back to slide, where was it? You just basically, it's looking up, like if you go back to slide 8, I won't do that because it'll take me forever to do this, but it's basically a catalog of the type of gate you have and what the G factor is. So for, regardless of where you are, what you do, and a G1 for a 2-input NAND is 4/3. So I just remember that. And
it's just like a catalog. Okay.
Yeah, it's just a catalog.
It's a set number.
Yeah, that's set.
It's a set number. Okay.
Yeah. And
that's nothing you calculated. It's in a table.
Exactly. And you can just look up table on page 8, and the table on page 9 shows you the parasitics for a similar thing. Now, the one caveat is that our claim was you would have designed this gate to have the same sort of drive ratio as an inverter. Okay, that means if you have like you sized a NAND gate in a weird way that you made the, say for the sake of discussions, the N's overly large compared to the P's, for whatever reason you did that, that wouldn't necessarily hold anymore, because if you remember, we were trying to ratio those sizes to be the same overall output resistance as an inverter that had a ratio of 2 to 1. So it's assuming that, but besides that, it's the same for that type of gate.
All right, thank you.
Sure. Okay, so let's see where, okay, so F120 is 125, okay? So we made the claim that, so now we want to know what's the best effort per stage, and we made the claim that if you have the overall number is F of 125, and we have 3 stages, so we have, this is 1 stage, this is the 2nd stage, this is the 3rd stage. We claimed that we would want to make the stage effort, if we made those all the same, they would give us the minimum delay, okay, or the minimum effort. Okay, so what am I saying? So another way to put it is that we're saying sorry guys, I'm just kind of figured out how to get my eraser to work in PowerPoint. So what I'm really claiming is that if I made F1, so remember F is per stage is G times H plus P for each stage, okay? So each one of these guys would have F1, F2, F3. So if I made F1 is equal to F2 is equal to F3, let's say they're all equal to an F, okay? If that's the case, we're gonna get the minimum delay, or we're gonna optimize how we get to this capital F. So if I look at that, remember this F is the multiplication of all these F's. So it ends up being F is F times small f times small f times small f. or f cubed. Then if you want to find the stage, the best stage effort, which is this f, or they call it sort of f hat, that is capital F to the 1/3. Okay. So this is the claim we made in the previous slide. Does everybody get how I got to that? That as long as, you know, we're making a claim that if you make the stage effort, all the stage efforts the same, you'll be an optimal scenario. And that means that each one will be F to the 1/3. Okay, that's, I think that's like the biggest one here. So anyway, so this, if I do this here, we end up with F to the 1/3 or 125 to the 1/3, and that is equal to 5. Okay, so F hat. Okay, so that's our optimal scenario per stage. Okay, now the parasitic delays. Okay, again, we have this catalog of parasitic delays. It's the parasitic delay of the first stage and the second stage and the third stage. Okay, so P1 for the parasitic delay for a 2-input NAND gate is 2, plus for 3-input NAND gate is 3. Again, this is going to slide 9. I'm just looking up in the table. And for a 2-input NOR gate is also 2, so that ends up being 7. Okay. All right. So what is the total delay? Remember that it is sort of the sum of the F's plus the sum of the P's. Okay, so we said here, we said each one of these is going to be 5. Okay, because that's where we calculated here. So, and we have 3 of them, plus our 7 from the parasitic value. It ends up being 22. Okay, so basically we're saying if you had this situation, okay, if you had, this is your situation here, right? So if I told you you had this situation in your hand with this load and this input, the fastest implementation of this path would give you a 22 delay implementation. So that, you know, if you let's say you were in, so if you multiplied this 22 by your process's tau, that would give you the delay for that stage. That's the optimal, that's the fastest you could implement that stage. Okay, so like remember tau, I think for 65 nanometer tau was 3 picoseconds or something like that, which would mean that the fastest we could implement this design or the delay through this stage in this design would be 66 picoseconds in a 65 nanometer process. That would be the fastest you could make it. Okay. Does that make sense, guys? So that's the first step. So now you know, okay, well, if I need to implement, so this, you know, sort of going back a few, I think maybe it was the first, the last face-to-face lecture we had, you know, I was talking about this is the kind of thing you want to do at the beginning of the project when you're scoping things out. If you know this is a particularly fast part of your circuit and you're worried about, hey, can I make the timing here? You can use this thing, which is kind of a back of the envelope calculation, and figure out if you can reach a particular speed, or what's the fastest speed you can get in a particular process. Do you need to go to another process, and so on? Okay, so that's this point. Okay, so that's the fastest delay we can do, is 22 Ds. And the D is, for each process, you're going to have a different actual delay. Okay, so the next step is, you know, after we know the fastest path is 22D, we want to figure out how to size the X. So we want to know how to size the gates. So we have a size for the first gate, which, you know, has an input capacitance of 8, but we don't have the sizes for the second and the third stage. And we know that the loading on the last stage is 45. Okay, so let's figure that out. So that's the next step. Sorry, that's going to be all the stuff in your lectures. Okay, so we calculated all that. Now we want to figure out, again, X and Y, how to size this stuff up. Okay, so what we do is we work backwards. Okay, so we said, whoops, why did I just do that? F is equal to G times H. Okay, so H, we know is, so let's start, so we're working backwards. So we're starting from this guy. Okay, we know that H there, so let's call this H3, call this H2, we call this H1. Okay, so we know H3 is 45 divided by this unknown that we're trying to calculate. Okay, so, but we know F, right? We said F per stage is 5 from the previous slide. So F is equal to 5 for the optimal speed. Okay, so 5 is equal to G times 45 over Y. And we know G because we have a 2-input NOR gate. And so we know the G of that is 5 over 3. So 5 is equal to 5 over 3, 45 over Y. So Y is, so the 5s go away, and you end up with 45 over 3, or 15. Okay, so we know Y is, it should be 50. So that's the best sizing for speed that you can do for Y. Okay, so now you want to go back, move one stage back to X, figure out what you need to size that guy up, and you do the same thing. So for X, so again, you have a situation where F is 5. And so because each stage we decided that the F we wanted to be the same. And that is G times H. You know, its output is now 15. It's plus, so conveniently these are both 15s, okay? So H2 here is 15 for the NOR gate that's in our path, plus 15 for the NOR gate that's not in our path, divided by x. Okay, so that's 30 over x that's H2. And the G for a 3-input NAND gate, we know is 5/3, again, looking it up in our table. And so X is, the 5s go away again. X is, did I do this right? 30. Yeah, so X is in, and then it ends up being 30 over 3. Okay. So did everybody see what I did there? Working backwards to get the sizing. So now, again, we know that the fastest delay you can have from A to B is 22 delay times. And the best sizing for that, if the size of the first NAND gate is, 8 size, the fastest sizing for the second gate is going to be 10, and for the third gate is going to be 15x. So that's kind of like a pretty powerful thing to be able to calculate pretty quickly. Again, anybody have any questions? It's kind of like probably one of the most confusing things in the class, calculation-wise. Okay. So let's see. Okay, so let's keep with this idea. So now, we saw how that's optimizing the delay. So, a powerful thing that comes out of the powerful realization from that comes out is, and you'll see this, there is an optimal way to drive a certain load. Okay. So let's say when we're talking about driving we have our chip, and we have a bunch of output pads. So you're driving another chip. So this is chip 1, this is chip 2. Okay, so we're driving another chip, and we know this has a total, some load capacitance. Okay, we want to figure out how to size the drivers on our first chip to drive this thing the fastest. Okay, so how many stages do we have to put in? And it turns out like that minimizing the number of stages does not minimize the delay, that there is an optimal delay, an optimal number of stages, okay, to drive it. So let's say we have the situation where we're trying to drive a load of 64x. Okay, and we're always starting with a 1x inverter. Okay, so we want to figure out what's the delay in each one of these implementation. Let's just using a 1x driver, or say 1 stage, 2 stage, 3 stage, 4 stage, etc. Is there an optimal size? Okay, so let's figure that out. So remember that we said that the delay is sort of the sum of the delays per stage, okay, plus the p's. Okay, and so we have n, so I'm trying to come up with an equation to describe all of these things. Okay, so in each case we'll have n stages. So for example, this here, n, so n here is equal to 1. There's just a single stage. So let me actually put it here so it's a little bit bigger. So in this one, n is 1. Okay, here in the second case, n is 2. We've got 2 stages. This one we have 3 inverters, so that's 3. And the last one we have 4 inverters, so that's n is equal to 4. Okay, and then we say, okay, the delay. We said the optimal delay is when the delay for each one of these is the same. So that's n stages times the overall effort divided by the number of stages. Okay, plus the total parasitic delays we have. Okay, so that's the equation we have for all these 4 cases, but in each one will give us a different d. Okay, so let's look at each case, right? So in the first case, F, okay, ends up being, we have a single stage, right? So, and the F is basically 64 divided by 1, okay, which is 64. Okay, so the delay ends up, and then we know that the P for a single inverter is 1. So basically delay ends up being 64 plus 1, so that's 65 in this case. Did everybody see what I just did? That makes sense? Jump in if it didn't, I guess. Okay, so let me do the second one. Let's see, so the second one, we have 2 stages, right? So we have 64 here, so for the second case, okay. We have 64, but this time because we have 2 stages, we get the square root of that, or 8 per stage. So each stage has an F of 8. Okay. So again, the delay ends up being, ends up being the number of stages times F plus the parasitics is 2. So this is overall is 18. Okay, so we see that 2 stages is significantly faster than 1 stage. Okay, as long as this is the ratio you're making between the first and the second stage. Okay, so let's look at having 3 stages. So here, third case, for 3 stages, we have 64. We have 3 stages, so we divide that in each stage, and that ends up being 4. Okay, so again, the delay is 3 times 4 plus, now we have 3 P's because we have 3 components, plus 3, so this is equal to 15. So 3 stages is better than 2 stages, better than 1 stage, so that's good. Okay, now let's look at 4 stages. So here, fourth case is 64 to the 1/4, which is around, it's like 2.82, so let's say 2.8. Okay, for F. And the delay ends up being 4 times 2.8 plus, we have 4 inverters, so it's plus 4. And this equals to, I have to actually calculate this with a calculator here. So it's 4 2.8 multiply 4 add, and it's 15.2. So 4 stages now, we didn't gain anything by going to 4 stages. In fact, it started slowing down again. Okay, so we see that if you have this, a particular load that you're trying to drive with a certain, input load, there's an optimal number of stages. In this case, it was 3 stages to get the fastest path to drive that load. Okay, did that make sense? Okay, again, it comes out of logical effort. And this is like one of the key things, by the way, to remember is that if you have a large load that you're trying to drive, you want to, doing it in one stage is not the fastest way to do it. You want to basically have this multi-stage driving function where you're stepping up the size of your devices. Okay. Okay. So, there's a derivation for this that I'm not going to go through because I'm like, it's kind of I feel it's a real made up way of looking at this, optimizing this delay or optimizing the sizing of the inverters. And I've seen a bunch of different ways to do this. This is one of them. But in either case, usually they don't get to a closed form solution. But I'll tell you guys the conclusion, which is always the same, that if you are trying to drive so if you have a large load, so again, in the case of let's say you have your chip's output pad. The reason I'm mentioning output pad is because that's usually the biggest capacitance that something on your chip will have to drive because it's driving something outside the chip. Okay, there's the next chip over and all this stuff behind it. There's an optimal sizing of inverters to drive this thing, and this optimal sizing is somewhere, and again, this is like a rule of thumb that's always good. This optimal sizing is between 2.4 and 6. Used to be people thought that it would be like E was optimal or 2.7, but when you look at the curve for optimizing that ratio over steps, it kind of is a flat curve, so you can really pick over a range. I typically pick at 3x. Our book is saying we should do 4x in sizing, meaning that, let's say you had a minimum size inverter, a 1x. You would want to drive the next one would be a 4x bigger size. Then you want to drive a 16x, etc. And that's the fastest ratio, depending on your load. You'd figure, okay, that load, the fastest thing that can drive that load is a 64x. And this is how I'm going to size these things going back. So I'd have 4 stages, and each one I need to increase in size by 4x. So that's sort of the thinking around there, which is this rule of thumb. So hopefully that made sense. So now if we, let me see if we're probably not going to have enough time to go back. So this was the example we were using as an overall effort so I think I'm gonna, guys, I think I'm gonna stop here because I think it's gonna take more than the 4 minutes that we have to look at this. But just as a reminder of what this was, oops, why did I just do that? That was a sign from God. Sorry. No, of course not. Let's see. Just 1 second, guys. Okay. So just as a reminder, we had the situation where we're trying to design a decoder to optimize the design of a decoder that is driving or selecting the bits in a register file, which is just a bunch of registers. And we're trying to optimize that. And, you know, we know the loading here. So we know that each of these words is 32 bits. And each one of these bits, each one of these memory elements has a loading of 3. So we know the overall loading is 96 per each one of these 16 channels. As a 96x load they need to drive. And we know that whatever's driving this decoder, we've been told that whatever's driving this thing can drive a 10x input. So the question is, knowing that, what's the optimal design here without actually, you know, putting the design together and simulating, etc.? Can we use this method of logical efforts, knowing the output load, knowing what the input capacitance can be, and the functionality, and figure out what's the optimal sizing? And that's the example I'm going to walk through sort of for next time. So we'll stop it right here. Any questions? I know that was you know, a lot of stuff and could be pretty confusing. Yeah, any questions, guys? All right. If there are any questions, please email me, and I'll try to get back to you guys fairly soon. So I'm going to put in the next lecture on this weekend, so recorded, and we'll start again with this example to use the logical efforts there. Okay, guys. Thanks a lot.
Thank you.
Thank you. Have a good one.
Bye.